Not this one. Green. All right, let's get started here. Hopefully you got your all submitted and you got the quiz submitted. Just a reminder, if you're just late on the OWL automatically does 10% within OWL, but in Canvas, if you're late, it's only 1.5% per day on that quiz or something. The take-home quizzes are 1.5% per day. Okay. So let's get started here. We'll do questions here. So we got 33 on this. Which of the following is written correctly? And the only way to do these is to really just start and look at all of them. So if we start with A, we've got PbCN4. Well, the CN here is cyanide, and this cyanide ion, we've got 4 of them. And 4 of them at -1 each gives us -4 on those 4 cyanides. That means lead would have to be a +4. This one looks good. There is a lead 4. That's good. That one looks good. If we did this one right here for letter B, this would be tin nitrite. Oops, NO2. There are 3 nitrites at -1 each, gives you -3. We'd have to have a +3 tin. No +3 tin, right? So this does not work. There is no +3 tin. In letter C, we have gold 3 or gold sulfide, some kind of gold sulfide. So sulfide is -2. So to get -2 out of these, what do we have to do? Like 2/3, huh? We'd have to be +2/3 or something like that on the gold. That would not work. In letter D, we have 2 ammoniums in parentheses. Ammoniums are +1 each. The PO4, I don't know if there's some way to get this, but that is phosphate. So that won't match. We've got a -3 and a +2. And in the last one, chromium This CN5 would give us a -5, so chromium would have to be a +5. Not -5, -1, but -5 total. I think the only one that works is A. Hopefully that's what I'll have for an answer then, because you got the answers for these afterwards. Yes. Yes. Okay, let's go to the quiz then. So for the quiz number 3. So number 3 is figuring out the average atomic mass using the percentages. So this would be 0.9051. When I change my percent to a decimal, the mass is 19.99 AMU. Then the next one is 0.27%. So I'm going to have to move the decimal to the left 2 places, times 20.99 plus we've got 9.2%, so 0.0922 times a mass of 21.99. That would do your weighted average. Hopefully that comes out to a correct answer. Does that work out? Yes, this one worked out? Okay. So that one there, 30, 23, and 25. 23 and 25. So 23, calculate the empirical formula. We're going to assume we've got 100 grams. We're going to, or 100 grams a sample. At these percentages, we can change these to grams. That's step 1. Step 2 is to convert to moles. So we've got grams of carbon, 12.01 grams, 1 mole. I'm going to write this smaller now, 8.7 grams of hydrogen. 0.01 grams of hydrogen and 1 mole of hydrogen, and 17.3 grams of nitrogen. And for nitrogen, 14.01 grams. Calculate the number of carbon atoms in the empirical formula. So after we get this, we have to divide by the smallest then. So we got to crank these out and then divide by the smallest. Okay, do we have to do step 4 on this? Or does it come out to be an even number for the carbon? Who's got this all worked out? Does it just come out even right away? Does it come out even right away? Who's got this worked out? Does it come out even right away? It comes out even right away. Thank you. So you don't have to do step 4. So once you divide by the smallest, you should have the answer for that. 25 is the same thing. We have percentages. It says, what is the total number of carbon, hydrogen, and oxygen in the empirical formula? So we're going to change all of these to grams, convert them to moles. So we'll get our moles. I'm going to crank this one through a little bit. That's going to be a little bit less than 5. It doesn't hurt to keep some extra numbers here. So 4.996. 4.436 2.219. Divide everything by the smallest, 2.219, 2.219, 2.219. This for sure is 1 for the oxygen. This looks to be 2. This looks to be 2.5. 2.25. So here's what we've got. We've got carbon at 5, hydrogen at 2, and at 1. So if we get 2.25, we got to multiply all to make them whole numbers, and we're going to multiply 2.25 by 4. We got to multiply everything by 4. So we are going to end up with C9H8O4. Looks like 9 plus 7. Looks like we get a total down here of 21. 21, so I'm hoping it was C. Let's continue now with chapter 3. The test is scheduled for October 10 or 11. I think we're on track to get there. Should be fine. So we're looking at October 10 or 11. I don't remember. 10, I think. I think the 10. Okay. So we wrote formulas of compounds. We're going to put these formulas of compounds into reactions, and we're going to identify what type of reactions we have. Then we're going to take those formulas of compounds, figure out our reactions, and then figure out quantitative numbers called stoichiometry. That's where we're going. Now, last time we balanced equations, and to balance equations, I have you do it in this order. I just think it works out the best. So balance equations in this order. Then we talked about at the end, in order to get ready for lab, we talked about electrolytes and non-electrolytes. Again, all of this work and the lab talk should have been the fact that water is polar. How is it that water is polar? There is not an even sharing of electrons in this bond. Water, oxygen is more electronegative than hydrogen. There's a tug of war for these shared electrons. Whichever one has the highest electronegativity wins. And the electronegativities are given on the back side of our periodic tables. Top right here, fluorine is the most electronegative element, 3.98. So whoever has the highest electronegativity is able to pull these shared electrons towards itself, and we assign them the negative charge. So in this case, we know that if I draw this as Mickey Mouse, the hydrogens get their electron pulled away. So the hydrogens are positive and the oxygen is negative. So we know positive here for the hydrogens and negative for the oxygen. That is polar. So that's how we actually assign charges or oxidation states that you find on your pink sheet. So, and we actually say that this electron gets completely pulled away from hydrogen. So hydrogen would have a +1 charge. Oxygen takes this electron from the hydrogen. It takes this electron from the hydrogen. So oxygen has gained how many electrons? 2, correct? So really, we can write the formula with H + 1, O - 2, and we get H2O, right? This also explains this freak in chemistry. It's difficult to teach because there's always exceptions. And you could have something like this. The electronegativity of fluorine is 3.98 and oxygen is 3.44. Which one wins the battle for the shared electrons? Fluorine. So then we end up with this +2 and -1. OF2, huh? The only time oxygen can be positive if we bond it to fluorine. That is the only time. It also explains this. +1 and -1. This is sodium hydride. Why do we assign hydride a -1? It's pulling the electrons away from the +1. Hydrogen is 2.20 and sodium is 0.93. So this chart would be no different than having a chart of magnetic pull from different magnetized elements or compounds, and they pull with different strengths, right? So electronegativity is the pull for shared electrons. So when we draw out water, and we're going to do this more in a later chapter, we say that there is an ion dipole attraction between water and a neighboring water or salts. So in lab, we explored why things dissolve, and I'm going to do that again some more. And we say that if water can pull the ions together, there's a dissociation. Okay, I'm still going to come back to equilibrium here coming up. So we know that if we get a bunch of ions in solution, it is a strong electrolyte. What is going to form electrolytes is ionic compounds that dissolve. Ionic compounds that dissolve are going to give these ions in solution. And when you did lab, you're going to get a high conductivity. So ionic compounds that dissolve. And we looked at this. Okay. Now, in section 3.5, we're going to talk about precipitation reactions or exchange reactions. Okay. For this, in order to just test what happens for exchange reactions, we just switch the positive ions. And then we evaluate a new interaction. So the positive ion A takes the place of positive ion C, and we're just switching these. So a balanced equation derived in the usual fashion is called a molecular equation because it doesn't explicitly represent the ionic species that are present in solution. When ionic compounds, again, what do you have for ionic compounds? Starts with a metal ion. Starts with a metal ion or ammonium, but typically metal ion, you can have ammonium. When ionic compounds dissolve in water, they may dissociate in their constituent ions. which are subsequently dispersed homogeneously throughout the resulting solution, explicitly representing all dissolved aqueous ions results in a complete ionic equation. The two chemical species present in identical form on both sides of the arrow or both sides of the reaction are called spectator ions. Ions whose presence is required to maintain charge neutrality are neither chemically nor physically changed by the process. And so they may be eliminated from the equation to yield a more succinct representation called a net ionic equation. A precipitation reaction is one in which dissolved substances react to form one or more solid products. Any reactions of this type involve the exchange of ions between ionic compounds in aqueous solution and are sometimes referred to as exchange reactions, or double displacement, or double replacement, or metathesis. All of these mean the same thing. Different ways to say the same reaction. The extent to which a substance may be dissolved in water or any solvent is quantitatively expressed as its solubility, defined as the maximum concentration of a substance that can be achieved under specific conditions, temperature and pressure. The units are grams in 100 grams of water. So when you talk solubility of salt, NaCl versus sugar, if you have 100 grams of water, you have 100 milliliters. Can you dissolve more sugar or more salt? What dissolves more, sugar or salt? Sugar. You can dissolve more sugar. And if you heat it up, you can dissolve a heck of a lot more sugar with increased temperature. Salt really doesn't change much as you heat the water solution up, but sugar, you can get a lot dissolved. Okay, let's look at an example. I want to show you exactly what we mean by an exchange reaction, which are beakers and everything. Okay, we have aqueous barium chloride in one beaker is dumped together with sodium sulfate in another beaker. Let's start this out. Aqueous barium chloride. So balanced complete reaction. So we're going to start right here, barium chloride. And we need to write that out correctly. Barium takes on a +2, chloride -1, so we get BaCl2 is aqueous. Aqueous means this dissolves in water solution. What does that look like? So I'm going to go down to here, this beaker right here. I'm going to fill it half full. I'm going to fill this one half full. What does that look like? Well, you've got barium in there, +2, surrounded by water with an orientation like this, because the negative oxygen is going to be attracted to the positive barium. So notice my positive ears of Mickey Mouse, which are positively charged, are facing away from there. There is an attraction between the negative oxygen and the positive barium. Then you have 2 Cl minuses in there. In this case, it's going to look like this. Where the positive hydrogens are going to be facing the negative ion. This is my barium chloride. Notice it is not Cl2. There's no such thing as Cl2. When you split these up into ions, It has to match what is on your ion pink sheet. It has to match. Can't invent ions. It does not exist. You will not find a Cl2 on this sheet anywhere. So make sure you split these up correctly. All right, so we got barium chloride. Now I'm going to color code these. I'm going to make the barium here pink and my barium pink here. We need to add to that sodium sulfate. Sodium +1, sulfate SO4 -2. So we need 2 sodiums, and this is aqueous. So what is that going to look like in the other beaker? Now this, oh, please do not split up the sulfate. This is going to split up into 2 sodiums. When this dissolves, we are going to get 2 sodiums. So I've got an Na+ here. I've got an Na+ there. And SO4 stays together. SO4 -2 stays together. SO4 -2 stays together as a sulfate. Do not create 4 oxides and a sulfur. SO4 stays together, just as it looks like on your pink sheet. Now, how is water going to be attracted to these? To have the positive hydrogens, the Mickey Mouse ears, facing away. For the negative sulfate, they would be facing in. I just put 4 around no matter what. Okay, I'm going to color code these a little bit better. I'm going to make my chlorides here yellow. And to green my sulfate. And I'm going to orange my sodium here. So I just color coded these. Now, on the back side of your periodic table is my solubility cheater grid. I call it a cheater grid because solubility rules from the textbook are given later on. We'll look at those. But grid out barium chloride on this backside, barium chloride. So if we grid out barium and we come down with chloride and we grid out barium chloride, we see AQ for aqueous, right? Barium chloride, aqueous. Similarly, with sodium sulfate, we're going to see aqueous. Now, what does that mean? That means water has the ability to surround this ionic compound and kind of start attaching itself to the positive and negatives as you see down here, and it can overpower the attractive force between the positive and negative ions here and separate them into individual ions that you cannot see with the naked eye. In the solid form, you would be able to see these. They would, both of these would be white. They would look like table salt. Now, you would probably agree that if I dump this beaker into this beaker, there's a new interaction that can take place. This positive barium might be able to hook up with this negative sulfate. And likewise, this positive sodium may be able to hook up with this negative chloride. So that is a new interaction that we need to explore. If the attractive force between the positive barium in this beaker and the negative sulfate in this beaker, if that attractive force between these two ions is really, really strong, they are going to come together, form a solid, drop to the bottom. If the attractive force is not strong enough, water is going to keep them suspended together. They can't come apart, no solid. So that's why what we do here is we exchange the positives. So we are going to exchange the positives. So barium is going to take the place of sodium. So now I'm going to have barium. Barium is where sodium is. So I'm going to have barium sulfate. +2 and -2. I just left this blank for now. Sodium is going to take the place of barium. This is +1 and -1. Now grid this out. What do you see for barium sulfate on your solubility chart? Grid this out on your pink sheet. Everybody grid this out. Everybody should have a pink sheet. Look at your pink sheet. Barium sulfate. We get an S right here. Yes, solid. Okay. We know that's going to be a solid. Sodium chloride better be AQ. Now, look at this. Sodium is AQ all the way across. We're not going to look up sodium anymore. We know that it's going to be just aqueous in solution. Potassium is the same way, AQ all the way across. We're not going to look those up anymore. Going down, acetates are pretty much aqueous. Bromides are aqueous, and so on. Iodides. Ones that are not aqueous, that form a lot of solids, would be hydroxides. Yes. Well, it's just Na. Yeah, and we're going to account for that. That's a good question. I didn't get to it. This has to be Na, one Na and one chloride because of +1 and -1. Now we need to balance it by doing what? We just need a 2 right here, right? We just need a 2. And that's going to take into account that. All right, so I want to make sure that here's my sulfate. Here's my chloride. Here's my sodium. And my barium. So now when I dump these together, I'm going to fill my beaker up to here because I'm going to I have half full, so I'm going to dump it up or fill it up here. What's going to happen is this. Your barium sulfate, it's going to end up as a solid precipitate. We would call this a precipitate on the bottom. There is my barium sulfate solid. What's still floating in solution? Invisible. Plus, in fact, 2 Na pluses, right? And 2 Cl minuses. This accounts for everything, correct? My barium here combines with the sulfate here, 1-to-1. We make barium sulfate. There's 2 chlorides in this beaker. There's 2 sodiums in this beaker. We still end up with ions stay in solution, right? What are these ions up here called? These are your spectator ions. So this first one up here is your molecular equation. I'm gonna make sure I kind of use what Al uses. This is my molecular equation, the first one. Now we're gonna do the complete ionic equation. And for your complete ionic equation, anything that is aqueous, we just split it up into its ions. We split it up into its ions, the same thing we did down here. So we're going to need all this room. I'm going way over to the left. When this splits up, we are going to get 2 bariums. We got to put AQ for aqueous. We get 2 chlorides. We get 2 sodiums. And we get sulfate. Making sure you have ion charges for everything. If you do not have ion charges for everything, you have to assume it's a neutral compound. Keep our barium sulfate together. Ions. And then here we are going to get 2 sodiums. We are going to get 2 chlorides. Boy, I made this. Why did I put that? 2 chlorides. Then we could just highlight our spectator ions. What's the same on both sides? Right? There's our spectator ions. If we cross out our spectator ions, so again, these are spectator ions. They're exactly the same, right? Just like algebra, you've got 2x on both sides of the equal sign, we're going to get rid of them. So we're going to eliminate out our spectator ions. I like to kind of put a little X over them if it shows up. I kind of like to do a little X. We put an X over them to eliminate them, and we finally end up with our net ionic equation. We crossed out matching ions of both sides, and we end up with Ba plus 2 aqueous plus SO4 minus 2 aqueous. Up with BaSO4 solid. This will be where our next lab, we're going to do solids in solution. Be aware, you can write some of this stuff out ahead of time for the lab on precipitates. Be aware, you can write some of that out ahead of time before you go to lab on precipitates. Okay. Double replacement reactions, exchange reactions, metathesis reactions, double displacement, it's all the same name. What do? Switch the positive ions. Switching the positive ions allows us to evaluate the interactions of whether or not we're going to get a solid. What does it mean when we get a solid? The attractive force between the positive and negative ions is so strong, water cannot keep them split apart. Okay. Let's go to the next page. I'm actually I'll come back to this. I've got an ugly owl question here. These, if I go to the bottom of page 9, the bottom of page 9 has solubility rules. Page 42 of your lab manual has solubility rules. So the solubility rules for ionic compounds in water, all sodium, potassium, ammonium salts are soluble. All nitrates, acetates, chlorates, perchlorates, salts are soluble. Notice these are negative ions, correct? If you look at the pink sheet, they're going to say AQs across either a row or column for these. All chlorides, bromides, iodines are soluble, except those containing lead, silver, and mercury are not. All sulfates are soluble, except. So there's always these exceptions. And there's kind of some contention. I say just give students a fancy table that tells you, because there's always these exceptions. Oh, that's all we're, oh, but there's this rule because it's chemistry, because nothing's ever 100%, right? So I kind of argue, I'm trying to argue that instead of kind of doing this, we give you a nice table that looks like this. You can just grid it out. Or on the very end, I've got another nice color table. So at the very end is another nice table that is similar to mine. It might have a few more, and it just tells you if it's soluble or not. Now, this table at the very end, soluble is what I put. This means AQ, so don't mix them up. I have AQ on my chart if it is soluble. So to me, I would like to just give you this grid. I don't know what's going to happen yet, but for sure, you don't want to look up sodium and potassium. You know it's soluble. You don't want to look up nitrates. Those are the ones I'll say we're not going to look up, but somehow it'd be nice to have a nice table like this that tells you whether or not it's dealing with all the exceptions. So they're probably going to use that table here. It's not on here. It might be on the last page. Okay. Writing net ionic equation. So we just did a big net ionic equation. It says write the reactions, write products by exchanging cations. These are positive ions. Dissociate, write as ions. All soluble salts, strong acids and strong bases. So we're just saying that you're going to split up soluble salts, aqueous, right? Aqueous. Strong acids. How you know we have an acid starts with hydrogen, right? And strong bases. Now, how do you know if you have a strong acid or base? This is what your textbook considers strong acids and strong bases. Again, what this means is we're going to split these up as aqueous. We're going to split these up as aqueous ions. Well, that means you're just going to split them up. Okay, here's an ugly owl question. So you've got zinc and you've got copper sulfate. This is a single replacement reaction, not a double replacement. We would call this single replacement. All right, so if this is aqueous, we would split these up, right? So let's see what we've got here. Let's just write it down here. So we've got zinc solid, it's going to stay together. This is aqueous. So we're going to have copper plus 2 aqueous, and we're going to have SO4 minus 2 aqueous. We've got an arrow. It tells us what is aqueous, right? We've got zinc plus 2 aqueous. And we've got SO4 minus 2 aqueous plus copper solid. Now, what is exactly the same on both sides? Sulfate. So if we cross out our sulfate as our spectator ions, it looks like we're going to have zinc solid. Bu plus 2 aqueous. Cn plus 2 aqueous. And copper solid. Okay, net ionic. We just canceled out ions that are the same. If it's aqueous, you're just going to split them up into individual ions, right? Split them up into individual ions. All right, let's go to the next page. This is another owl question. It looks like I got 3 owls in a row. It says, write the net ionic equation for the following molecular equation. HCl is a strong electrolyte. HNO2 is a weak electrolyte. These are acids, right? Both of these are acids, start with hydrogen. So this is a strong acid. If that is a strong acid, you're going to make it ions. Aqueous, but you need to make this into ions. I'm going to put 100% split. into ions. Now, HCl is a strong electrolyte. HNO2 is a weak electrolyte. Notice though, in my formula here, it is still aqueous. And this is the definition of a weak electrolyte, how many ions you're going to get? Maybe 5 out of 100. You're going to get a few ions, right? But you get very few ions. So do not split. But it still says it's aqueous because it's still dissolved in water. This is like sugar. You still write sugar as aqueous, but you don't split up all the carbons, hydrogen, and oxygens. Okay, so let's come over here. Is potassium nitrite going to split up? Potassium nitrite, for sure. It starts with potassium. So we're going to split this up into K plus aqueous. This is going to be NO2 minus aqueous. Cl is a strong acid. So this is going to break up into H plus aqueous and Cl minus aqueous. Arrow. Is KCl going to split up? Oh, heck yeah. It starts with potassium. Remember, sodium and potassiums are going to split up. Nitrates are going to split up. Those you want to you're not even going to look up sodium, potassiums, and nitrates, 100%. So we're going to split this up into K plus aqueous and Cl minus aqueous. HNO2, if it's not a strong acid, you have to keep it together. HNO2, but it's still aqueous. We do not split it up. Now, what do we get for spectator ions that are the same? K plus, K plus. So this is an exact OWL question. Or it's going to be very, very similar. So what do we have left? It's like we've got NO2 minus. And we have H plus. H. NO2 aqueous. And the last box can be left blank. All right, another OWL question. Potassium cyanide. So we need the formula for potassium cyanide. So on your pink sheet, let's write it out right here. What's potassium cyanide for a formula? A is potassium cyanide minus 1. It says an aqueous solution. Is that going to split up? Sure, this is going to split up into ions. It starts with potassium. So we know that this is going to be aqueous. Let's write split here as we're looking. Hydrochloric acid. What's the formula for hydrochloric acid? HCl. We know it's aqueous. It's in water solution. Are we going to split it up? So if you don't know for sure, go to your chart here If it's on the strong acid list, we split it up. Right here are going to be 100% split. Right here are going to be 100% split. If it's on this list, split it up 100%. How do you know if you have a base? Ends in OH. Hydroxides are bases. Hydroxides. For now, hydroxides. So if it's on the list as a strong acid, we are going to split them up. So HCl is a strong acid. We're going to split. An aqueous solution of potassium chloride, a hydrocyanic acid results. So let's do this right here. Well, I guess we can write it out like this. Potassium chloride, let's write that out right here. That's going to be KCl. Is it going to split? Yes. Starts with potassium. Hydrocyanic acid. Hydrocyanic acid. It's an acid, starts with hydrogen. And we need cyanide. +1, -1. This is still aqueous. It's in water solution. It's an acid. Is it going to split? Is it on the list for strong acids? No split. No. No split. It's not a strong acid. So that pretty much then, let's split them up right here. We're going to have, I'm going to start right here. We've got K plus, aqueous. We've got Cn minus, aqueous. Split up HCl into H plus aqueous, Cl minus aqueous. Ooh. You know what? We should have wrote that out as one big reaction first before we split everything up to balance it. I got lucky here because everything's +1, -1. Be careful if we do it. If you do it this way, if they don't, you might have to balance it. KCl is going to split up. So we get K plus, aqueous, Cl minus, aqueous. Then the HCN is going to stay together. It is still aqueous. It's still in water solution, but we won't split it up. So spectator ions. Looks like we've got K plus, Cl minus. And it looks like we can fill it in. So we did 3 OWL questions. They should match up pretty much what you end up opening in OWL. They should match up pretty darn well. Okay, now we're going to look at types of reactions. Do we have synthesis, decomposition, single replacement, double replacement? Do we have combustions? Are we getting precipitate, acid base, oxidation reduction? We're going to predict whether or not we get solids out like what we did earlier, and identify some common acids and bases. Again, this is some more solubility rules. I think, I don't remember if I grabbed this exact one from the book. I don't remember. I don't think so. But these are some of these we're not going to look up. We're going to know sodium. You got to remember sodium, potassium, ammonium is going to dissolve. And then nitrates, chlorates, perchlorates, acetates, these pretty much dissolve. Now you end up with this, almost all. So chlorides, bromides, iodides dissolve. These are the exceptions. Salts containing fluoride, most dissolve. Here's these exceptions. See, there's always these exceptions. So we just have a grid to look at, like what's on the backside of the pink sheet. It works out pretty well. Sulfates, most sulfates are soluble. These are some exceptions. Soluble compounds, negative ions. And of course, the ones that are exceptions are the ones that are over here: sodium, potassium, ammonium. And again, this is solubility down here. Some more guidelines, but all right, let's look at this. Soluble compounds are defined as those that dissolve to the extent of 1 gram or more per 100 gram of water. Not soluble compounds are further classified as slightly soluble, which dissolve to the extent of 0.01 grams to 1 gram. And difficult solubility or insoluble, which is less than 0.01. So you might see the term soluble, slightly soluble, or insoluble. So soluble, slightly soluble, or insoluble. Okay, let's go to this page right here. Let's see. Let's do one where we write them out. Let's do C. So first of all, let's write this out. It says write balanced net ionic equations for the reaction. So if we write out lead to nitrate, got enough room, let's do, this is going to be PV plus 2, nitrate NO3 minus 1. So we can go like this. Can I put AQ? Is that going to split up in water? Yeah, why? Because it's nitrate, right? It's a nitrate. Just nitrates are going to split up. Aqueous plus KCl plus 1 minus 1. Is that going to split up? Heck yeah, sodium and potassium. Put an AQ there. Now let's switch the positives. So if we switch the positives, lead takes the place of potassium. So lead is with the chloride now. So we're going to need PbCl2. Let's leave that blank. We don't know for sure if it's aqueous because it's not a sodium, potassium, lithium nitrate, right? So let's just leave it blank. And then potassium takes the place of lead. So we're going to end up with K plus 1, NO3 minus 1. Is this aqueous? Heck yeah, probably the most aqueous salt you can make. It starts with potassium, ends in nitrate. They're both super, super soluble, aqueous. What about this? Lead-2 chloride. Well, let's try these rules. Look at this one. Almost all salts of chlorides, bromides, iodides are soluble. Exceptions are silver, mercury 1, and lead. So this is not soluble. And if you grid it out on the cheater sheet, as I call it, lead-2 chloride. Where is it? Lead-2 chloride. Is it lead-2 chloride? Yeah, lead-2 chloride. Lead-2 chloride, that's for a solid right here. So we know this is a solid. What do we got to do next? We need to balance this. So what do we need to do to balance it? We would start with the nitrates. We got 2 nitrates here. We've got 1 nitrate here. We need to put a 2 here. And for chlorides, we got 2 chlorides there. So once we do, I should do this in order. I apologize. Let me back up. You get 2 nitrates, 1 nitrate. Start with parentheses, and then look for metals. 1 potassium is a metal, so we've got 2 potassiums here, 1 here. Need to put a 2. The other metal is lead. 1 to 1, we're good. Non-metals, chlorides are good. That looks good. Okay, so we need a net ionic equation out of this. So if we split this up, we're going to end up with Pb plus 2 aqueous, 2 nitrates. Two potassiums, 2 chlorides. PbCl2 has to stay together as a solid. We're going to get 2 potassiums here. If you do not have your charges up above, everything is not correct. If you do not have charges, we're assuming you have neutral compounds. So make sure everything has a charge if it's supposed to have a charge or an oxidation state. So why don't we cross out our spectator ions? The light X over our spectator ions. And then we can just box in our net ionic with a different colors. So Pb plus 2, 2 chlorides. There's our net ionic, right? All right. Another owl question. Lots of owl questions, but this is pretty much going to get us through owl part 1 for chapter 3. Does a reaction occur? Potassium hydroxide KOH, aqueous, is it going to split? For sure, starts with potassium, right? Split. Cobalt 2 sulfite, sulfate. Is that going to split? It's a sulfate. Yes, there are a few exceptions, but this is going to split. We can grid it out. So we'll go down here then. So we have KOH with plus cobalt 2 sulfate. I shouldn't put parentheses around that. Cobalt 2 sulfate. Can I write aqueous for that? Heck yeah, starts with potassium, aqueous. Switch that, we get cobalt hydroxide. So it's going to take 2 hydroxides. Solid or aqueous for cobalt 2 hydroxide? Cobalt 2 hydroxide. You can look at the rules. You can look at your cheater grid. Cobalt 2 hydroxide, solid. Does the reaction occur? The answer now is yes. Yes. We need to balance this with a 2 right there. And then you would finish that and write that out. That kind of gets us through OWL part 1. And OWL part 2 does acids, and we already named acids. So you can poke into OWL chapter 3 part 2 as well, do some naming acids. But this pretty much goes through OWL chapter 3 part 1. It gets you into chapter 3 part 2. For the quiz, let me have you look at some quiz questions here. 1 through 12, you can try on the quiz now. 1 through 12, you should be able to do a lot. You should be able to complete all now of OWL chapter 3 part 1, and you can poke into chapter 3 part 2 again because it starts with naming acids, and we already did that. In fact, a lot of it's just naming acids, so you're going to be able to cruise through that. All right, have a great weekend.